All right, let's look at a couple things today. First of all, this is the homework we're going to have up here on this screen. All right, it'll be asked this question a lot of times. Is this function, this graph, is it even, odd, or neither? Even, odd, or neither? What about this one? What about this one? What about those? Okay, so that's what you're going to be looking at today. A couple of things there. All right, now, first thing I want you to notice is, let's do this. Let's do some graphing. Type this in, ABS, and then parentheses. This is one way that you can type in absolute value. So ABS, parentheses, and then X. All right, let's do another one. Next one. Let's do X squared. Okay, let's do another one. Let's do X squared minus 5. And let's do one last one. X to the 4th minus 3x squared. So we've got 4 graphs on there. They all have something in common. And I'm looking for somebody to tell me, what do all 4 of those have in common?
Ooh.
Yes.
X.
Okay. Anything else? Yeah. Yeah, very good. So if you take a look at all these graphs, all of them can be reflected right across this line. And when we do that, they match on the other side, right? So for example, whoa, it's locked in. Whoa. All right. So here's what I mean. There's a point right here that's, not quite to 3 and about 2.8 up here, right? If we go over to the other side, that same point is there, right? If we look at something like 2, 4, there's a point right here at 2, 4 that the blue and the purple graph are on. All right. If you look at this point, 2, 4, and you look at this point, negative 2, 4, you can make a claim here. You could say that this is the same as this. There's some symmetry, right? They're the same distance from the y-axis. All right. So these will have something in common. Any guess as to what we call these kind of functions? Hint. It's one of these 3 things. We can classify all of these functions as one of those words. Even. Doesn't it just kind of make sense, right? What happens on one side is the same as what happens on the other. They are even, right? Literally, they're even with each other. This y-coordinate is the same as this. This y-coordinate's the same as this. This y-coordinate's the same as this, right? And on down the line. They all match. They're even with each other across the y-axis. All of these are examples. Now, let me show you something that doesn't quite work. Right, x minus 5 squared is this one over here. Right? Try that on your screen. X minus 5 in parentheses, and then square that one. Now, looking at that parabola, it's the same shape as the blue graph on your screen, right? X squared. It's the same shape. But this one cannot be counted as even. Why?
It doesn't reflect.
Yeah, it doesn't reflect over what?
Why?
The y-axis, right? Now, you could make your own line of reflection like right down the middle of it, but it doesn't reflect over the y-axis. So, what can we say about even graphs? Well, we can say if there's a certain x over here, like this one, 3, 4, if it's even, the same point will be on the negative side, right? At negative 3, 4. For some reason, it won't spot up on there. Right? And it is. It just won't zoom in far enough. So these are all even graphs except for the black graph right here. All right, let's try some more. Let me show you something else. Any guesses as to what we could type in for an odd graph? Here were some of the things we used for even graphs. All the things we use for even graphs are up on your screen. Take a look at what they have in common. Okay. Okay. You could use positives, but they'll have an exponent. Be more specific.
Squared.
Okay. And what kind of number is squared?
If you put an odd next.
Oh, okay. So what if we use an odd exponent? All right, let's take a look at it. X to the third. Okay, x to the third, why don't you clear all those and just do x to the third. So x cubed is an S curve, and it is an odd function. Here's another odd function. Let's do this. Try x to the third minus 2x. That's an odd function. Let's do another one. Anybody want to throw out a guess as another odd function? Make one up real quick. Come on. X to the fifth. Okay. Guess what? You can add this onto it. X to the minus x to the. So we got x to the fifth. You could say then minus x to the what? Third. And then what else could you add? Plus, let's say 4x. Let's try that. Guess what? That's also odd. It's very funky looking, but it is odd. Now, guess what? How do we make an odd function? Well, it's the opposite of what it means to be even. So take a look up here on my screen now. On this blue curve, there's a point right here at 2, 4. If I go over to negative 2, it's not up here at 4. That was if it was even, right? They were straight across from each other. They were literally even with each other horizontally. Then, this one's an odd function. So if I go to 2, 4, there's a point. Where will it be if I go to negative 2? It'll be at negative 4. That's what an odd function does. So if we use the opposite x's, you will end up with what kind of y's? The same? The opposite. Thank you. All right, so how about here? This point is at 1, 1. Since it's an odd graph, and we know that, there will be a point where? Instead of at positive 1, there'll be one at negative 1, negative 1. Okay? If I zoom out, here's a point right here at 1, 4 on the green graph. If I go over to negative 1, yeah, negative 1, negative 4. Okay? The opposite x coordinate will give you the opposite y coordinate. Now, how do I make one of these odd ones not odd anymore? Well, check this out. What do you think I could introduce into the equation? Yeah, some kind of even exponent like this. So if I do that, let's zoom in on this red one. This is no longer an odd function. Now here's why. If I take a look at this point right here, there is not a version of it that is somewhere over here, right? This point does not have a counterpart that has a point of positive 2/3, negative 0.148. There's no counterpart to it. There's no symmetry. Okay, so let me erase that again. There's something that we have here, and it is a kind of symmetry, but it's not the symmetry that we had earlier with evens. Okay, it's a symmetry called origin symmetry. And what that means is if you rotate it around the origin 180 degrees like this, watch, like this, right? You have to make that noise, but don't spit on anybody. Okay, rotate 180. Guess what? You end up with symmetry there, right? Rotate it. Rotational symmetry. If I do that with either one of these graphs, if I rotate this part up here 180, guess what? It matches exactly down below. That's what creates an odd function. So if I want to destroy that symmetry, I can introduce an even number exponent. Now it doesn't have that symmetry anymore. Here's the other thing that you didn't notice. What if I just add on a number? So like on this first one, this red graph, it's just x cubed. What if I shift it up 5? That's what we've been talking about lately. Is this still odd? In other words, does it have rotational symmetry around the origin? So you could check it like this. This point, if I rotate it 180 degrees, does it have a counterpart down here at -5? Does that point exist on this curve? No, it doesn't, right? So if I vertical shift an odd function, it's no longer odd. But if I introduce another odd exponent, it'll be just fine, right? So you could make a guess as to how you can determine what an odd function is. We can keep doing this, right? X to the 19th. Very funky, but there it is. Green one, still odd. Very weird looking, but odd function. So if we take a look at this first example from Kahn right here. Function f is graphed according to the graph. Is f even, odd, or neither? Easy enough, right? This is even. There's symmetry across the y-axis. We look at any one of these points. There's a point there. It has a counterpart there. There is no violation of that either. There is an exact symmetrical relationship between the right side and left side, right? Okay, next one. How about this? Even, odd, or neither? This is neither. If it's even, this point would have a counterpart over here, right? It doesn't, so it's not even. If it's odd, there would be this exact point at about 3, 7-ish. At -3, -7. Is there a point there? No. If you can find one counterexample, then it's not odd. All right? So one thing that has to be true about all odd functions, generally, I need to think of exceptions, but this point here has to be there. There must be a point at the origin. Think about it. If it's going to have rotational symmetry around the origin, there better be a point at the origin. Now, it could be that there's some kind of discontinuity like this sort of thing, but we're not going to see many of those, right? So this isn't odd. It's neither. All right, how about this one? Even, odd, or neither? This one is odd. What have we noticed about all odd equations? Odd exponents. Do they have any even exponents? No. And they also can't have a number on the end. If I do that, now it becomes neither. Okay? Here's what most people forget about numbers added onto something, right? You could think of a number, like let's say I added 5 onto this, as having how many x's? So 5. is the same thing as 5 times x to the not first, because then it would be 1. 0, right? There's 0 x's there. Now, this helps us because if I see a constant added on, then I can think of the exponent 0 as being what kind of number? Just like the number 10. Is 10 even or odd? It's even, right? It's got a 0 on the end, right? So if you see a number on the end, this is evidence for an even function, or it might make an odd function, neither. Okay, so you need to look out for that. Let's try out this table. We haven't seen any table questions yet. According to the table, is this function even, odd, or neither? Now keep this in mind. An even function, if you plug in a certain x, you get f of x, right? You get a certain y coordinate. If you plug in the opposite of x, you get the same y coordinate. They're at the same height, right? So when I plug in one x and I plug in the opposite of that, they should be equal to each other. If they are opposites, then they're odd, right? Like this. So if I plug in an x, I get this y coordinate. If I plug in this x, I get this y coordinate, but it's the opposite. This is an odd function. So let's look at the table. I plug in -4 and I get -5. What do I get when I plug in +4? +5. Those are opposites, aren't they? Let's confirm the rest of the table, though, because we don't want one counterexample to mess it all up. If we plug in -2, do we get the same thing? Or sorry, do we get the opposite of what we got when we plugged in +2? Yeah, they're opposites. That tells me that this thing is odd. What would the table look like if it was even? Well, -4 would be 5. 4 would be, what if it was even, I'm saying? If it was even graph. Remember, an even graph will have the same y coordinates, right? The exact same. So if we plug in -4 and 4, they would both give us 5. They'd have the same y coordinates. If I plug in -2 and let's say I got -1, what would be the solution for 2? It'd be still -1, right? They have to match up. This would be an example of an even table. All the y's would be the same when you compare their opposites. They have to match exactly. This one's odd. When you think of this column as, this row as y's instead of f of x, I think it can help you visualize it a little better. All right, let's try this one. I didn't put the colors on there. This one's the blue. Is this one odd or even? It's even, right? You can see two different reasons why. It has all even exponents, and we can see the symmetry here, right? If you need to use Desmos on one of these assignments, you may. All right, the green one is the second one, right? Is the green one odd or even? It is also even, right? It has the same symmetry. Each one of these is an even exponent. Remember, I talked about a number having 0 x's, right? These are both even exponents, even though there's nothing here. Those are both even. All right, you'll have 2 assignments today. I'm going to add them here real quick.